In October 2023, the UK government officially cancelled the northern extensions of HS2, the 2010 vision of an expansive £20 billion Y network reaching Manchester and Leeds has shrunk to a single trunk line between London and the West Midlands. Meanwhile, estimated costs for this remaining section have surged past £87 billion. This political turbulence obscures the actual engineering rationale. The primary purpose of HS2 is to relieve the mathematically exhausted West Coast Main Line. Europe's busiest mixed-use railway forces 125-mile-per-hour intercity expresses to share legacy Victorian tracks with slower regional commuter services and heavy freight. This mix of speeds creates massive operational bottlenecks, capping the total volume of trains the network can physically handle. By constructing a brand-new, dedicated high-speed line for intercity travel, those express trains are removed from the existing tracks. This provides the slot capacity required to run dramatically more local passenger and freight services. Moving those express services requires rolling stock operating at 360 kilometers per hour. Speeds at this threshold subject the physical track to intense dynamic forces and severe load stresses. To safely maintain these velocities, the track geometry faces brutal constraints. Gradients are strictly capped between 1 and 2.5%, and the paths must remain exceptionally straight. That rigid mathematical formula immediately collides with the rolling, unpredictable topography of the English countryside. Enforcing that flat, straight trajectory through valleys and hills requires over 32 miles of excavated tunnels and the construction of more than 50 major viaducts. Maintaining millimeter-level structural tolerances across 140 miles of linear infrastructure requires an uncompromising quality assurance ecosystem to verify every stage of the build. HS2 operates under the strict legal parameters of the NEC4 suite, the new engineering and contract framework. This contractual foundation enforces a definitive structural separation between the entities physically building the railway and the engineers verifying its quality. HS2 Limited delegates physical construction to Tier 1 joint ventures, assigning structural verification to an independent NEC supervisor node. These quality engineers maintain a constant presence across work phases, holding legal authority to monitor progress and issue defect notifications directly to construction joint ventures. Every action on site is evaluated against the HS2 specification for civil engineering works. The contractors cannot grade their own work. By embedding this separation into the contract, quality control ceases to be an administrative checklist. It operates as a continuous, legally binding structural audit. The mechanism driving these audits is the Inspection and Test Plan, or ITP. Every physical activity is governed by a specific ITP matrix. This flowchart tracks how risk is managed on site. The critical structural operations are designated as hold points. At these markers, construction is legally paralyzed until both the contractor's team and the independent supervisor physically inspect the work and input their sign-offs. For example, before crews can pour concrete into a viaduct pier formwork, an engineer must verify the density, the precise tensioning, and the exact steel spacing. Other tasks are designated as witness points. If an air test is scheduled for a newly laid drainage line, the supervisor is notified. If they are absent, the contractor can proceed, but they must fully document the test results. This oversight reaches deep into the supply chain through aggressive material traceability protocols for prefabricated components.
Consider a single precast concrete segment used to line a tunnel. It is stamped with a unique identifier that links it to its exact aggregate mix batch, the specific date it was cast, and the results of its 28-day compressive strength tests. The ITP matrix removes assumption. Every component acquires an audited structural pedigree before it ever absorbs a dynamic load. The physical assurance of the railway begins below the surface, deep within the geotechnical earthworks. If the soil beneath a train traveling at 360 kilometers per hour settles unevenly, the geometry of the track will fail. To prevent this, site crews use nuclear density gauges to test the moisture condition value and the maximum dry density of the embankments, strictly controlling the compaction limits. Above ground, the threat profile changes. In massive concrete pours for station foundations and bridge abutments, chemical hydration generates immense internal heat. If the internal core expands from this heat, while the external surface cools and contracts, the concrete experiences thermal shock, leading to deep internal cracking. This diagram demonstrates the engineering countermeasure. Thermal couplers are embedded deep within the concrete to continuously monitor the delta T, the exact temperature differential between the core and the outer surface. By analyzing this differential, engineers adapt curing rates in real time to prevent microscopic structural failures from initiating. Ultimately, field-level quality control actively monitors these invisible thermodynamic and geotechnical variables every single day to ensure total structural integrity. Attempting to log thousands of daily density tests, thermal readings, and ITP hold points on paper would instantly paralyze a 140-mile construction site. To solve this, HS2 uses integrated common data environments. Engineers use ruggedized tablets to instantly upload field data and geotagged photographs from the active workface. The ultimate verification step validates the final, built physical structure against its theoretical design. This visualization shows the validation process. Terrestrial laser scanners and drones capture high-density point cloud data of the as-built asset, which is then overlaid directly onto the 3D building information model. If a newly constructed pile or concrete edge deviates past the millimeter-level tolerance of the design, the system instantly flags the structural deviation. Subsequent work is halted until the discrepancy is resolved. This digital feedback loop forces the physical reality of the concrete and steel to match the mathematical precision of the engineering models. Despite these controls, isolated failures, such as a concrete batch failing a slump test or weld porosity caught during an X-ray, still occur on a megaproject of this scale. When an error is detected, a non-conformance report is automatically generated. Work on that specific asset is halted immediately while structural engineers trace the root cause. This diagram illustrates the system-wide adaptation. The root cause analysis feeds into the project's learning legacy framework, which then pushes updated inspection protocols out to the active ITPs across all joint ventures. By instantly distributing the solution, the network ensures that a localized failure cannot repeat and scale into a systemic risk. The political scope of High-Speed 2 has been heavily reduced since its inception. The engineering standards have not. The dramatic capacity increase on the legacy network will be the direct result of millions of mathematically verified, perfectly tracked data points.